When I first introduced this idea of entropy, I said, wow, this is something that's going to be really, really useful. And so far, all we've really done is said, okay, entropy is a property. We went through some logic to come up with that. Whatever, it's a property. We can look it up. That's nice. It's tabulated. We don't have to go measure it. But how useful has it been? Because all I've really done is shown you how to find entropy changes of solids, liquids, and ideal gases. So what does that have to do with the efficiency of a pump or, a turbine, for example, and how good it is? Well, the ideal situation for the majority of engineering systems like pumps and turbines and nozzles and diffusers and all those things is that they operate isentropically. In other words, that as the fluid moves through them, the entropy of that fluid does not change. Think about it. If you have a pump and that pump has some friction in it, what's going to happen is the entropy of the liquid, let's say, being moved through that pump is going to change because heat will be transferred into that liquid. Therefore, entropy will be transferred into that liquid, and the entropy of the liquid will increase. Ultimately, what this means is you paid for some work to put into the pump that did something you didn't really want to do. Your goal in buying the pump was not to heat up the liquid, right? Your goal in buying the pump was to pressurize the liquid. And so some of the energy you had to put into the pump went into increasing the thermal energy of the fluid flowing through it. And that is not ideal. That's not why you pay for energy, to drive a pump. So all of these engineering devices ideally operate at no entropy change. So what if let's back up for a second. Instead of talking about a liquid pump, let's think about turbines and compressors and nozzles, diffusers, things that operate with gases. And in particular, let's consider items that operate with ideal gases, because that's a good place to start. If you think about a turbocharger for a car, for example, it really consists of a turbine and a compressor wheel, and both of those operate with gases that are essentially ideal gases. And so what if we did have an ideal turbocharger? Well, then the compressor side would have the same entropy of the entering air as the exiting air. There'd be no irreversibilities in that compressor wheel. And so the incoming and exiting entropy of the stream that's flowing through it would be the same, and the difference, therefore, would be zero. And that's what we've got here. We've got the entropy change for an ideal gas equation. We've selected one of them, the one that has, constant volume, heat capacity, and volume in the last term. And we've set it equal to zero. Not that it's always zero, but ideally we want our devices to operate with no entropy generation, and therefore constant entropy. So set it equal to zero because we're trying to come up with equations that model what ideal systems can do. So if we start playing around with this mathematically and we realize that, well, we've got two terms that are, the opposite of one another, then we can move one term to the other side just by changing the sign on it. And since we don't like negative signs, why don't we remember some rules of natural logs and logarithms in general, and remember that we can take that negative sign and raise it as an exponent on the argument, that volume ratio V2 over V1. And so ultimately what that does is it just flips the ratio, right? So we got V1 over V2 instead of V2 over V1. Then if we continue playing with this a little bit, we could put the constants all together, like the gas constant and the constant volume heat capacity. We can put all those together on one side of the equation. And then if we consider what's going on here, we've got the natural logarithm of two things, right? And the natural logarithm of those two things are equal, therefore those two things themselves are equal. But before we get ahead of ourselves, notice that heat capacity at constant pressure is heat capacity at constant volume plus the gas constant. And also we can define the ratio of the heat capacity at constant pressure to the heat capacity at constant volume as a symbol K. If you have forgotten, you might want to go to the back of your book in the appendices at this point. First page, I don't care if you go to metric or English appendices, and you'll notice that on the facing page, the right hand side, they've got K listed for a bunch of gases. So they've got CP, they got CV, and they got K. You might take a couple of those and just see that this works. If you take CP over CV for one given gas, you'll find that it's just K that is tabulated. So you don't actually have to do this. But if you put these things together, these two equations, with a little bit of algebra, will tell you that that exponent of R over CV is simply K minus 1. And it's just a little bit different way of writing it. And so ultimately what we end up with is these two arguments inside the natural log are equal to each other. And oh, by the way, the exponent R over CV is just K minus 1. And notice that there is a subscript on the left-hand side of the temperature ratio equation. It says S equals constant. In other words, for constant entropy. Well, how did that come into play? Well, that's where we set S2 minus S1 equals 0. We're trying to come up with an equation that models what happens when a device is isentropic, when that device is ideal. And that's what this equation does. It says if you had a nozzle or diffuser and you tell me the temperature at the entrance and exit, I can tell you what the volume, the specific volume ratio across that device should be if it's operating perfectly as a completely reversible device. And that would be the best we could ever hope for. So if you understand all that math, that's great. If you don't worry about it. Here's what you really need to know. This is the so-called first isentropic relationship, and it applies to a lot of different equipment. I've already mentioned nozzles and diffusers, but it also applies to turbines and compressors. Well, almost. There's a device on this page that it does not apply to. Do you know which one it is? Pause the video and think for a minute. Remember some of the restrictions on the equation. What were the restrictions? The restrictions were that this had to be isentropic. What does it mean for something to be isentropic? Well, it has to be reversible and adiabatic. If a process is reversible and adiabatic, then it is isentropic. But guess what? Our compressor is not adiabatic. Look, there's heat transfer. There's heat flowing out of the compressor. Now, there are good reasons for having heat flow out of a compressor as it compresses a gas. It has to do with something I'll talk about in a little bit, how ultimately you're going to lose the energy anyway, so you may as well do it when it benefits. But for right now, just realize that this isentropic equation can't apply to this particular compressor on the upper right-hand side that has air flowing through it at a rate of 0.02 kilograms per second, because it's not isentropic. And the way I know that is because I see heat transfer there. Therefore, it's not adiabatic, and so therefore the entropy of the air flowing through it is going to change. As a matter of fact, if heat flows out, ideally the entropy of the air would go down, right? Because remember, heat carries entropy with it. And so the amount of work you have to put in would be even less because, well, we'll get into that in a little bit. So anyway, the point is, this is the first isentropic relation. It doesn't apply if you have heat transfer in the device, and there are restrictions on it. Number one, this only can deal with ideal gases. If a gas is behaving in a real way, in a non-ideal way, then this equation won't work, because remember, we use the ideal gas law to derive it. There has to be constant heat capacity. Now, just looking at the equation, you might not remember that, because the heat capacity is hidden away in K. Remember, K is the ratio of heat capacity, Cp over Cv. And when you take a ratio and you say that ratio is a number and I'm done, you've inherently said that the heat capacities are constant, right? So this will only work when T1 and T2 are relatively close to one another. It's also only good for isentropic processes, and that means when the process is adiabatic, no heat transfer, and reversible, in other words, ideal. With all those restrictions, we can use this so-called first isentropic relation. At this point, you should go to the back of the chapter and look for this first isentropic relation. Turns out there's 3 of them. You'll see the rest here in the slides in a moment. And they're all equally valid and useful. They all say the same thing, just in different ways. But note the restrictions on this. In fact, you should look for these restrictions in the text around the equations, because again, it's not really obvious from the way that your author writes the equations and the notes he puts around them as to what the restrictions are on the various equations. So make sure you highlight them and you know when you can and when you cannot use this. Obviously, you can't use this on a liquid, so don't even try. It won't work. Okay? Now, there were actually 2 equations that were kind of similar, right? For ideal gases, they were for calculating entropy changes of ideal gases. Here's the other one. It involved the constant pressure heat capacity and a ratio of pressures. If we play the same game with this that we played with the last one, saying, well, what happens in the ideal situation where the device does not increase or decrease entropy at all, the entropy remains constant as the ideal gas flows through the device, then we would set this one equal to 0 as well. Notice that there's no negative sign, so there's no need to flip the pressure ratio, and we just end up putting the constants R and Cp together, and we're farther along quicker than we were before. We end up here at this equation where again we're trying to talk about just the arguments of the natural logarithms themselves, the T2 over T1 and the P2 over P1 to the R over Cp. we'll invoke the two relations we had before for K, the ratio of heat capacities, and Cp equals Cv plus R. Again, it's a little bit of algebra, but you can show that R over Cp is K minus 1 over K. And we always like writing our exponents this way. So we end up with another isentropic equation relating the temperature at the entrance and exit of a device to the pressure ratio at the entrance and exit of that device and the ratio of heat capacities K. Once again, if you understand all the math, that's great. If you don't, it's okay. Here's the point of what we've done. We've derived this equation that is really useful. It's useful for all these devices, except again for the one that has heat transfer in it, because this is again an equation that deals with constant entropy processes. Now be careful. One thing you'll want to note about these equations we're deriving, these three isentropic relations, is that the ratio T2 over T1, those temperatures, have to be in absolute units or this will not work. You probably should write a note for yourself next to the three equations in the back of the chapter so you don't forget it in the stress and fog of an exam. But which one should you use? This one, or the first, or the third, which we haven't quite gotten to yet? Just use whichever one's most convenient. If you're given pressures and you're trying to find temperatures, use this one. If you're given volumes and you're trying to find temperatures, use the last one, the first isentropic relation. The restrictions on them all are the same. This only works for ideal gases, relatively small temperature ranges so that the heat capacity can be constant, and for adiabatic, in other words no heat transfer, reversible and therefore isentropic processes. But it's known as the second isentropic relation. Now you might have noticed that the first and second isentropic relation look a lot alike, right? The left-hand side, in fact, is identical, and therefore can't we set the right-hand sides equal to each other? Well, yes, in fact, we can. You'll notice also that the exponents simplify just a little bit. We've got a K minus 1 in both cases that cancel, and we can, of course, move the remaining 1 over K on the pressure ratio over to the volume as just K, and we end up with the so-called third isentropic relation. It's derived from the first and the second. So again, if we're not dealing with anything that involves temperature and we need to relate pressures and volumes across an ideal system or device, well then this is a go-to equation that should work if we're dealing with ideal gases. Now obviously it still doesn't work when there's any heat transfer into or out of the system, and all the restrictions of the other two equations apply to this as well. But it's nice to have three different equations that are all equally valid, and you just pick whichever one is most convenient for you. And you can use it and it'll work just fine as long as you know the restrictions on it.